Wow, this is fantastic. After months and months and months of planning, just seeing all of you here, we're really excited. We've got a very diverse group of people here in attendance as well as on stage to be speaking over the next couple of days. We have individuals who have flown from as far away from Tokyo, from Stockholm, all across the states, and of course, everyone here from my hometown, New York City. Is Brooklyn in the house? Yes, exactly. All right, cool. So we are starting a little bit late, but it's okay because we could catch up pretty nicely. I'm not going to stay on too long. Just wanted to point out a couple of things. First off, there's a mezzanine level with entrances, and you guys could totally get in up there as well and out. And second thing is just have a great time. I hope you learn lots and have lots of fun. So without further ado, I'd just like to introduce Basho's Chief Technical Officer, Justin Sheehy. He's going to give some opening remarks. So welcome to Recon.
I'm going to keep this pretty short to try to get us on schedule, but mostly I just wanted to thank you all for coming out here, whether you're a speaker, an attendee, folks from Fastly, everybody that's making this possible. When we had the first Recon last year, it was a wild success, beyond my dreams, maybe not beyond Mark's, because he's probably, I think, better at dreaming than I am. But the big reason it was a success is that I felt, accelerated the conversation going on between people building distributed systems right now. And that set of people is getting a lot bigger, right? I think Mark Cavaj from Joyent was pointing out the other day, it doesn't matter who you are, you're going to be building a distributed system sooner or later. But that set of people that have to do that, the technology element getting bigger, doesn't make a community. To make a community, we need conversations. And that's what this is about. And there's a lot of different ways that those of us building these things can have conversations, right? Some of it is through code. And we try to do a lot of our development in the open, right? Even between people at Basho, sending each other pull requests as a way to do development. Doing more and more of all of our work in open source when it makes sense as part of how we all do what we do. A lot of these conversations get created by the best people that we know, bringing their content, their way of speaking, their way of thinking to the rest of us. And that's one of the things we're trying to create an opportunity here for on stage. But a lot of the even better conversations are the ones that you don't know who they're going to come from. And they don't happen on stage, they happen between stages. And that's the thing I really hope we've created an opportunity here for. The people that would never have known to look to each other, talk to each other, will, in fact, over these next 2 days, have a 2-day conversation with each other. And the reason I keep going on and on about conversation is I think it's the best way to learn, right? It's by talking with people and listening to people. And that's why this is very much, even though we put it on and we name it kind of after our product, it's not a product conference, right? We've done this. We've invited people here to talk about software that does things we can't do. We've invited people here to talk about how they tear our software apart and make it do horrible things. Or to come talk to us about ideas we couldn't have had, right? Those are the conversations that we're here to learn from, and I'm here to learn from. And so I want to thank every single one of you for making that possible. And speaking of people to learn from, I have the great privilege to introduce our first speaker. Margo Seltzer has been, if you are one of the kinds of people who would come here, she has been a creator of some software that has benefited you. Whether we're talking about file systems, Berkeley DB, so many things over the past few decades that in storage, in databases that Margo has mattered to. And she's gone on to now become in a role that I think epitomizes the kind of conversation we want. She's both at Harvard, serving as a professor, working on scalable data, provenance, other hard, interesting problems, and being an architect at Oracle, helping to keep guiding and leading forward some of the software she helped to create much earlier. And so I really have, I would like to be here to see all of these talks. I think there's a great deal of people here that I want to learn from, but I would have made the trip here just to listen to Margo. So please welcome Margo Seltzer.
Thanks, Justin. Are we good on sound? Okay. So here's the deal. I'm going to try to use the little fancy remote. It's going to work for about 10 slides, then it's going to break. I'll curse, and we'll go on. It happens every time. So one of the great things about being a professor is that these wide-eyed graduate students show up with these great ideas, and they don't know what's impossible. And so the work I'm going to talk about was actually the brainchild of Amos Waterland, who's one of my students. Came about from conversations he had with Jonathan Apavu when they were both at IBM. And then he dragged in my other student, Elaine Angelino. And again, walked in with this grand vision of how we're going to make computation scalable. Didn't realize that, of course, no one could do that. And so he, of course, proceeded to go ahead and do it. So ever since we built the second computer, people have had this fantasy about being able to parallelize programs and make programs run on lots of computers. And we've seen parallel languages, and we've seen parallel runtimes, and it's still really, really hard to take a sequential program and actually run it on lots of computers. So wouldn't it be cool if you could just take your sequential program, wave a magic wand, and this is where the computer stops working. Usually we get more slides than that. OK. So you wave a magic wand, and then all of a sudden your program runs on millions and millions of cores. So that's the vision that we want to try to make happen. So in order to make that happen, I'm going to ask you to engage in the following thought experiment. I want you to think of a simple processor as consisting of some very simple state, right? It's got a set of registers, and it's got some memory. And we can take those memory and those registers and sort of stack them up, and we can think of that as comprising a state space. Okay? Now, it's a really big state space, right? You've got tens or hundreds of registers. You've got potentially gigabytes of memory. So it's a really big state space, but you can think of it as a state space. So if we think about it as a state space, then what does computation look like? Well, you start out by initializing this state by loading in a program and some data. And for now, we're going to forget about I/O. So you load in a program and some data. And once you do that, then your execution is completely defined by that initial state, right? The instruction pointer points to some instruction, and you know that what you do is you execute that instruction, and that induces a change in the state, and it advances the instruction pointer, and then you do another instruction, and that's another change in state. So if we think about the memory and registers of our processor as comprising this really large state space, then what does a program execution become? Well, it becomes just a walk through this state space. So at every instruction, you take a little tiny step, and each instruction only changes the state a little bit. And you start when you load your program and data, and then you run until you get to some state that's defined to be an end state, and your program is done. So visually, you might think of it as this, not so random, but a deterministic walk through a very high-dimensional state space. Fair enough? Maybe? All right. So now the question is, if I wanted to parallelize this, how would I do it? You say, oh, well, that's pretty easy. What I'm going to do is I'm going to pick equidistant points in that state space. And then what I can do is I can dispatch a core on each of those states. And then each of those cores can start executing from the state that I give it. And what we've ended up doing is we sort of execute in 1 over n of the time. So if I have 8 processors here, I just executed in 1/8 of the time, and I executed all the instructions in my program. So that's fabulous, right? So there we go. That's how you do it. That's how you parallelize a program. You guys are laughing. You're saying, but wait a minute. So if I could do that, now wait, it gets even better, right? That was 1 over n scalability. But if I can actually predict those states, well, heck, why don't I just predict the end state, and then I can have infinite speed up. So this is where we want to go. Now, you might think for a moment that this is perhaps not possible. And OK, I'll concede a little bit. It's not entirely possible. But imagine that I could make some guesses. So each of these little fuzzy things are probability distributions. So let's say that I can't guess the trajectory perfectly. But let's say for a moment, bear with me, that I could guess places you're likely to be. Well, if I could make those guesses, then what might I do? Well, I might send messages to all my little cores and say, hey, we have some guesses where you might be. Pick one of those guesses, and now start executing. And so the red circle is the real program, and it's going to execute the real instructions, okay? And every so often, it's going to stop, and it's going to say, hey, guys, has anybody been in this state before? And if none of you say anything, it'll say, oh, OK, I'll keep executing. And it'll go on. It'll say, has anyone been here? And you notice we're really close. But close isn't good enough. He goes, OK, I'll keep executing. And then he gets here, and he says, wait a minute. Has anybody been here? And suddenly, this processor chimes in and says, yeah, I have. Now, once you know that he started executing from the same state you're in, you know exactly where you're going to end up sometime in the future. And for the purposes of now, think of sometime in the future as, tens of thousands of instructions. So not a huge long time, but a while. So since I know that, I can just race right to the end. I don't have to execute it. I just ask him, where did you end up? And I jump to it. And then I keep, hey, has anybody been here? And I ask here and say, has anybody been here? And the answer is sure, yep. So now what I've done is I've taken this ridiculous problem of having to predict accurately where I end up and turned it into a slightly less ridiculous problem of having to make some guesses. And if the guesses turn out to be right, then I can get this speed up. So I know what you're thinking. You're thinking, you must be kidding me. This is not something that we could really do, is it? I mean, how are you possibly going to guess places in the trajectory? Right? Come on, give me a break, And how does that red guy even know when to check? Even if you guessed places, how would the red guy know where you guessed and know how to jump there? And these states, they're enormous. Like, by the time you finish comparing the state to see if it's the same, y'all could have just executed all the instructions anyway, so why bother? Or maybe you're saying, how do you store these computations, right? So all your workers go off and they execute for a while, and they have to store this somehow? How do you do that? But remember, you guys are all storage guys, so that's your problem. And finally, you're just sitting there going, are you on drugs? So I'm actually not on drugs, a little scotch perhaps, but not drugs. And I'm not actually kidding. So I'm going to come back to this chart at the end of the talk. But these are real live results from a system we've built. And what it is we've got a number of cores along the bottom in a log scale, and the speed up we get in a log scale vertically. So if we got perfect speed up, we'd be on the green line. And we're not. And that's how you know this is a real system. If I were faking the numbers, we'd be on the green line. But we're not. We're the blue circles. And you might say, well, the blue circles aren't the green line. And it's true, but we're getting scalability up to like 256 or 512, even a little bit up to 2K. Right? This is a program that was compiled with your friend GCC, no parallelization, no magic. We take a regular program, we run it in our little virtual machine, and we get that kind of speed up. So I think that's pretty cool. OK, so how can this possibly be? It all comes down to the ability to make predictions. And so the question you should be asking me is, OK, that little silly blue trajectory line, what does that look like for real programs? Now, if I told you that it looks like this, with a nice straight line, then all of us in the room could sit down and write predictors and say, ooh, at instruction N, I know exactly where I'm going to be, and we'd be great. So that would be good news. If, however, I said this is what programs look like, and I gave you a random trajectory, then you're going to look at me and say, good luck. Come back here, in a decade or two. But the reality is that real programs don't look like either of those. Real programs look something like this. They have kind of a recognizable pattern. They do kind of the same things over and over again. Now, why is that? And I claim it's because programs are actually like people. People get stuck in ruts, right? Okay, how many of you go to the same coffee shop every single day? That's up. Come on, there's audience participation. Raise your hand. I know you're out there. OK, so you might think that your activities on a day-to-day basis are, your own decision. But I'm going to say that with high probability, I can predict where you'll be at 10 a.m. or 2 a.m. or 11 a.m. based on where you were yesterday and stuff like that. So people are predictable. Turns out programs are predictable too, right? They do things like this. For I equals 1 to a gazillion, do something. Well, I can pretty much predict where you're going to be for a gazillion different times. So maybe there's something to this prediction. What else do programs do? Programs do stuff like this, and they call subroutines or functions. Well, OK, I might be able to predict what functions you're going to call. So maybe I'm not totally on drugs. maybe programs are predictable enough that we could actually do this. So if you wanted to do this, the question is, how would you build such a system? So what I'm going to do is I'm going to show you a general architecture for automatically scalable computation, and then I'll tell you the particular implementation we built. But the message is that it's a general architecture. You could all go off and build your own. And then we could come back next year and we could compare them and see how they do. And that would be fun. So we start out with an execution engine, which we call a trajectory-based execution engine, because it's built along this line that you're moving in this state space. So we'll talk about how we do that. Then you have this thing we call a recognizer, and its sole purpose in life is to look at the program as it's running and say, where are some good locations that I might be able to predict? Right? And the recognizer could be a person, right? Somebody could hand annotate, right? If you were going to hand annotate places to predict, you might predict the beginnings of functions, the top of loops, things like that. It could be the compiler helping you do that, or it could be a learner, which is what we do. Once you've picked some good places to predict, you tell the execution engine about it and say, hey, keep track of these locations for me. Okay. Then what you do is you hand off these locations to the predictors, and you say, here, every time we end up at this particular point in the program, the point represented by a value of the instruction pointer, right? Every time we're at this exact same point in the program, we're going to show you what the state looks like. And the predictor's job is to take a sequence of those states and then make predictions about what the system might look like the next time you get there. Yeah, good luck, right? And then what it's going to do is say, okay, here's a bunch of predictions. It'll send it off to an allocator. And the allocator is going to send it off, and it's going to start speculating. So as many cores as you have at your disposal, the allocator will take these predictions and say, here, you start executing there, you start executing there. And every once in a while, and execute for this long. And when you're done, put your entry in this trajectory cache so that our little execution engine here can periodically say, has anyone been here? And if it says, has anyone been here, then you get a hit, and then we jump ahead. So is everybody with me on what this looks like? Great. How many of you think we can actually build it? All right, I got one vote of confidence. That's good. So before we get into how we build it, let's ask the question, how good do our predictions have to be? Right? It would be nice to know that. So on the x-axis here, we've got how good our predictions are. So how accurate are our predictions? And on the y-axis, we've got some number of cores. And then each of these lines says, what kind of speed up do you get? So for example, if my predictor gets it right 1 out of 5 times, it's 20% accurate, and I have 80 cores, then you get a 10x speed up, or a little bit more than that, because we're above that 10x curve. And you say, well, that kind of sucks, Margo. You got 80 cores, and you're only getting a 10x speed up. But imagine for a moment that, in a couple of years, you have 128 cores on your laptop, which you will. Can you use them? I suppose if you want to browse 128 pages simultaneously, maybe. But I'm going to guess that most of those cores are usually idle. So if I could take 80 of them and make your compiles run 10 times faster, that might not be so bad. So that's actually not terrible. But let's imagine we can get our predictive accuracy up to 40%. Now we get a 30x speed up. And of course, if I can predict perfectly, then I get a perfect speed up. But I don't think we're going to get there. So that's what we're shooting for. Yeah, question?
When you're measuring predictive accuracy, what's the ratio? What is it?
So I'm saying I tell 100 cores to go out and make predictions about where I'm going to be enough in the future that I can take advantage of it. And if 4 of them give me correct locations, or 40 out of those 100, that's a 40% accuracy.
So you're talking about, okay, so it's the number of times you actually use the predictive cache.
Yes.
The number of things you store.
Yeah, you can think of it as the hit rate of my predictive cache. Okay? And people should feel free to ask questions, because I want everybody following this along so you can go ooh and ah when we get to the final results. Yeah.
Are you segmenting the state space at all? Just your register or just?
So hold that thought. I'll get to it in just a minute. Okay, so let me go on to how we actually build this, and then we can take some more questions. So what I'll do is I'll talk you through, at a very high level, how we implement each of these pieces, and then I'll dive into each of them so you get a sense of what we're really doing. So our trajectory-based execution engine is this little virtual machine. It's very stupid. It's entirely in software, but it treats the whole thing as a bit vector. Yeah, a really, really big bit vector. And it just executes instructions. our recognizer looks for IP values that happen often enough and are easily predictable. Now, for a predictor, we actually have a set of predictors. And the way that the system is set up is you can plug in as many predictors as you want, and the allocator actually can take those predictors and, on a bit-by-bit basis, guarantee that we do at least as well as the best predictor for that bit. Okay, again, we'll go into this in more detail, but just giving you the overview. So the allocator takes the predictions, takes the predictions from the various predictors, produces some number of predictors that it can then speculate on, and we speculate using the exact same VM that we use for execution. And then we build this distributed cache. Does that sound like a storage problem? Such that a little bit of the cache lives on each core. Okay, so that's what our system's going to look like. Now we'll talk about the pieces, and if when I get through the VM I haven't answered your question, raise your hand again. So here's our VM. What it does is it takes all the registers and all the memory that we have, and it casts it into this big bit vector. Big bit vector. Now the good news, even though the bit vector is really big, each instruction only touches a few bits, and even a long-running program doesn't touch the whole space, right? The program, we don't do self-modifying code, so all the program stuff stays the same. That never changes. In a lot of applications, you know, you get some input data. That doesn't change. So the amount of state that actually changes is many, many orders of magnitude smaller than the total state. So that's the good news, right? This is what is starting to make it tractable. So what the VM does is it takes the bit vector in, it knows what the instruction pointer is, and so it goes and it looks at the instruction that lives there, figures out how to execute it, and it produces an output bit vector. So instead of having sort of what you think of as a simple simulation loop, it has one function inside, which is, you know, transform. Take this vector, transform it into the output vector, and then what do? I take the output vector and I feed it back in. And so all our little VM does is it says, oh, I know what to do when I see this vector. I produce this next state. Oh, here's a state. Here's the next state. And so this VM just walks through the state space. Does that answer your question? OK. All right, next we have to build a recognizer. So what the recognizer is looking for is it's looking for one or more good instruction pointer values that are predictable. As we said, beginnings of functions, loops, stuff like that. So what it does is it takes any random, the first value of the instruction pointer it sees, and it says, I wonder if I can predict it. And then it waits for a while. And it would like to see another value of that instruction pointer. Because if it doesn't, then it has no hope of building a model off of only one point. So it says, I'll try another IP. Here's another one. And then it waits for a while. It says, ooh, I just saw it again. Now I have 2 points. And we all know that once you have 2 data points, you can perfectly predict anything because you get a line. So every time the recognizer starts to see repeated values in the instruction pointer, so it starts to observe some structure in the program, it takes advantage of its friends, the predictors, right? We've got predictors in this system. And what we're trying to do is find values that are easy to predict. OK, I guess we'll just try to predict them. So for each IP value, it goes and sends off to one of the cores and it says, here's an IP value. I've seen it twice. See if you can predict the next one. And it does that with as many IP values as it's run into. And it gives it to all the predictors. And the predictors come back and say, well, I think you'll see this state, and here's how certain I am you'll see this state. So they actually give a probability with that. And the next time the recognizer sees that state, he goes, wow, your prediction was right on. I like you. I think that's a good IP value. That's the one we're going to start to track. Now, you could build a recognizer that tracks many different IP values. At the moment, we only track one. So that's how we figure out where we're going to start tracking. And then we have a collection of predictors. So the predictors, this is, we wrote a paper on this, and one of the reviewers described it as, oh, they try to do something with parallelization, and then they sprinkle machine learning pixie dust on it and assume it's all going to work. So this is the machine learning pixie dust. So we have a structure that lets us have as many different predictors as we want. And then we have a way of combining them. And so I'll talk about this in 2 pieces. First the predictors, and then how we combine them. So we started out with 2 blindingly simple and stupid predictors called weatherman and mean. The weatherman is like the weatherman. If it's sunny today, it's going to be sunny tomorrow. If it's cloudy today, it will be cloudy tomorrow. So the weatherman predictor always predicts that the next bit, that the bit in the next iteration will be exactly the same as it was in this one. So if the bit was a 1, it will always be a 1. If it was a 0, it will be a 0 tomorrow. And the weatherman is happy to change its mind when the bit becomes 0. Okay? Really dumb predictor actually works remarkably well in certain things. Turns out certain status bits in the status register don't change very much. Turns out weatherman works great for that. Okay, so that's our weatherman predictor. The mean is a little smarter. It keeps track of what it sees over time, and it picks the average value. So if the bit's usually a 1, the mean predictor will predict a 1. If it's usually a 0, it will predict a 0. Okay, so those are the stupid ones. What's funny about it is that, we built those because they were easy, and then we started doing the evaluation. We said, oh, we're not going to use those. Those are too stupid. Turns out they're really useful for certain bits. So we use them all. Okay, then we have 2 slightly more clever ones. But I want to say these are actually really the easy machine learning algorithms, right? Like, these are like the first 2 things you learn about when you take a machine learning course. There's nothing complicated here. We can build arbitrarily complicated predictors, but we haven't yet. So these are actually pretty simple ones. The first one is still going to do bit-level predictions, and it's called a logistic regressor. And so it's also a 1-layer neural net, if that makes more sense to you. The way to think about it is that if you start with a bit vector, each bit in the next state is some function of potentially all the bits in the bit vector. Now, we know that not all of them actually contribute. So what you're doing over time is for every bit in the output vector, you're learning weights on which bits in the input vector influence it. And so every time you see another state, those weights get better and better until you start to predict things. So that's what our logistic regressor does. And then we have a linear regression. So I hope at some point somebody in here is thinking, why the hell are you doing this on the bit level? Right? You know that most of these things are 32-bit registers, so wouldn't it be easier to predict those? And the answer is sometimes. And so we do have a linear regressor, which essentially tries to fit 32-bit values to a curve. So what is that good for? Well, think about your loop variable, right? For I equals 1 to a gazillion, that one's really, really predictable as a 32-bit value. Not so much as individual bits. But we can predict that as a 32-bit value pretty easily. So the goal is that we have different predictors that work well for different kinds of parts of the state. And if we're clever, the goal is that we can combine all these predictors and different bits and actually do a good job overall. Some of you are still skeptical. Yeah?
So at this point, what you're doing is you're creating, you're sort of over time generating a mapping of your state space to predictors that you use for parts of that state space.
Yes, I think that's right. I'll phrase it slightly differently. So what we're doing over time is we're building a model for every single bit in the state space. We're building a model that, based on the history you've seen up until now, will predict the next bit. And we build a different model for every single bit in that space. Now, it might be that 32 of the bits are well predicted by the linear regressor, and that's fine, but we have a bit-by-bit model of what they're going to look like. Does this sound insane? Good, good. The first time we submitted a paper on this, we literally got a reviewer comment that said, this is borderline crazy. It's exactly where I wanted to be. It's exactly where I wanted to be. All right, so we've got predictors. Now the question is, how do I combine these predictions to do anything useful? So let's imagine, so here's our allocator, and he's got these 4 different predictors. What he's going to do is he's going to assign a weight to each of the predictors for each bit. So I'm going to show you what happens for 1 bit. Just repeat this a gazillion times for each bit in the state. So he says, OK, I'm going to start out, and I don't know anything about these guys, so I'm going to start them all out with weight 1. And then I'm going to say, so I'm going to look and see what did they predict for the little bit that's in red. And it turns out that 3 of them actually predicted a 1, and 1 of them predicted a 0. So he says, well, OK, I like Weatherman, mean, and linear regressor. They're all pretty good. But Mr. Logistic kind of sucks. So what I'm going to do is I'm going to cut his weight in half. And then I'm going to say, all right, so now I have weights. I'm going to ask each of you, tell me what you think the next value of the bit will be. So they say, OK, here's what we think the next value is. And so what he does is he looks at his 4 predictors and he says, well, there's a weight of 2 that says the next bit's going to be a 1, because there's 2 people voting for 1, and they each have weight 1. So there's a weight of 2 that says it'll be 1. And there's a weight of 1.5 that says it'll be 0. So our allocator says, I'm going to predict a 1, because that's what my predictors tell me. So we predict a 1, and it turns out we're wrong. Bummer. He says, OK, well, let's try again. So now he says, OK, let's look at what you guys did. I've got to update your weights. So Weatherman and Mean, you were both wrong here, and I trusted you, too. Whoa, sorry. All right, so I trusted you. So I'm going to have to penalize you and cut your weights down, too. But the other guy, their weights get to stay the same. And so what we're doing is, over time, we're trying to get a sense of which of these predictors predicts this bit. So say, OK, next predictions. And now we get 3 zeros and a 1. If we add the weights up, the weight on 0 is 2, right? We got the 2.5s and the 1. And the weight, so this one looks pretty likely to be a 0. And sure enough, when we go to the next state, it's a 0. So what we see happening when we run this is that if you've got something like a counter variable, then pretty quickly, the 3 top predictors, they all go to almost 0. And the linear guy is pretty good. We can extrapolate a straight line really well. For bits in the status register, we often see that either Weatherman or Mean end up working pretty well. And so over time, different bits in the vector end up using different predictors. And what's really nice about this structure, oops, I didn't show you that. Okay, what's really nice about the way we combine these is that we guarantee that our overall prediction is always at least as good, if not better, than the best predictor. So what that means is you can keep throwing different predictors at the problem, and it can't hurt you. It can only make things better. And if you have 2 predictors that work pretty well, then what you'll find is that you do better than either of them would have done independently. Does that make sense? Questions there? Yeah? So we don't explicitly keep track of it, but for each bit, we have the weights. So in fact, when we analyze this, we go back and we look at those weights and figure it out. But it doesn't, in real time, it's just keeping track of the weights. It's not saying, oh, this is the right predictor. Does that make sense? Any other questions? OK. So now we've got these predictions. We have to figure out how to run them. So we have the speculator. Now, I said that the speculator was just another instance of our virtual machine. And that's true, but there's one other fact that you should know. Our virtual machine can track dependencies while it runs. So what does that mean? Well, what I want to do is I want to keep track of all the values that got read and all the values that got written. Because it turns out that if you go off and execute a few tens or even hundreds of thousands of instructions, you only touch a teeny, teeny fraction of the state space. So when I put things in my cache, I really only want to put those teeny, teeny fractions. I don't want to put the whole vectors in. So that's what this dependency tracking is going to have to do. So let's imagine that our state vector is that tiny vector up there. And the instruction we want to do is we want to add 8 into the value stored at address A. So in order to execute that instruction, I'm going to have to read 3 fields here. Hello. OK? So I'm going to read the fields that correspond to the IP. I'm going to read the 8 bits of constant, the value 8, which is 4 bits of constant. And I'm going to read the value that's stored at address A. So this read mask is going to tell me which bits matter. If there's not a 1 in the read mask, then I don't care what the values are. And then I'm going to store the first values I ever read. So in this read vector, I'm going to say, OK, here are the bits I cared about, and these were what their values were the first time I ever read them. And all I care about is that first time. Now I execute the instruction. And so we increment the instruction pointer, and we change the value that's stored in A. So now what I want to do is I want to say, OK, which bits are part of the output of this computation? So I start forming a write mask. So the write mask is going to have a 1 anytime I update bit values. And then I say, OK, and when I run, I want to keep track of the last value that I wrote. So the last value I wrote is right here. And then you execute some arbitrary number of times, and you keep track of all the bits you ever read and the initial values of those bits. And you keep track of which values get written and the final values of those. And we call that a cache entry. Now, what does the cache entry really tell us? What it says is that in order to match on a state, I actually don't have to match every single bit in this gazillion bit vector. I only have to match on the ones I read. Here's another way to think about it. Imagine that the speculation is a function call. You really only care about the parameters to the function call. So those are the things that are going to get read. And then, what gets written? Well, the final result gets written. So if I keep track of where I started and where I end up, that's exactly enough information to be able to fast forward the main thread. So let's look at how we use the trajectory cache. So each core that does any of this speculation keeps track of its own cache entries. Okay, so we have a distributed cache. And each cache entry essentially captures the information I described, the 2-bit masks and the 2-value masks. So now when the master comes along and says, hey, has anybody seen this state? Here's what's going on. Master says, here's a new state that I'm in. Can anybody match it? And so the first entry says, well, in order for me to match, you would have to have identical bits to what's in my read value register everywhere that I've got a 1 in the mask register. So, ooh, I can actually use the fancy. No, can't use that either. Maybe, wait a minute. It could be good for something. Okay, so basically it says all these bits here have to match. So do they? Well, let's see. Here's the bit pattern here. That doesn't match at all. So that's a miss. So, okay, let me check the next entry. Well, let's see here. What do you have to match on? Well, you have to match all these bits, and the values are right here. So, ooh, look, the instruction pointer is the same, and this value is the same. Yay, we have a hit. So even though the rest of those bits may be totally different than the state we were in when we created this cache entry, this is still a cache hit, because the computation expressed by that cache entry depends only on those 2 fields. So if it depends only on those 2 fields, how do I calculate the output bit vector? Well, I know which bits got written. So I take the result of my write, and I put that into the output vector. And then I have a couple other bits that got written, and I put those in. All the other bits didn't get written when I created this entry. So they're going to be exactly the same, and they're just going to come from the state we started in. And so what we've done is we've used this cache entry to fast forward a computation, and that computation may have actually been in a slightly different state. Right? The way to think about this, if you think about those trajectory pictures, right? What you're doing is you're taking a subsegment of a trajectory and you're translating it. You're saying, okay, you computed it here, but the line looks like this, and we're just going to do a translation and move it into somebody else's trajectory. So this solves a bunch of the problems we were worried about. Number 1, the cache entries are much smaller than the overall state. And number 2, they match on many more states than just the one that created them. And this is what's actually going to give us the ability to make reasonable predictions. So, here's the overall picture of what we've done. And ideally, you're sitting there going, yeah, but how well does it work? Like, does it really work? And the answer is it really kind of does. It's kind of cool. So here's the picture I showed you at the beginning, and now I'll tell you a little bit more about this program. So first of all, this is a real-life program that our friends in physics came to us with. So I'm not sure how they get started, but ultimately, they have these kinematic simulations. And so they start out, and they create this linked list of a bunch of points. And what they're trying to do is find points that are below some threshold. So overall, what the main program does, which is the top bit of code, is that it iterates over this linked list. And for each element in the linked list, referenced by the node variable, it says, please go compute the potential. That's going to give you an energy. And if the energy is less than some threshold, then you're done. Now, on one hand, this is really parallelizable. right? You just take each entry in the list and you throw it off to lots of processors and life is good. In practice, this is exactly the kind of problem that compilers don't do very well because you're traversing a linked list. And the compiler has no idea where you're going to be at the 5,000th element of the list until it sees the 4,999th pointer. So the compiler can't really help you here. You could hire a programmer to parallelize it, but physicists are cheap and they don't want to do that. And they really don't like to have to tailor their applications for every hardware platform. So they want to just take their sequential program and say, make it parallel. Now, there's another feature of this program that is interesting to us. Here's the potential function. And the bottom line is it's really slow. It takes a long time to compute the energy of one of these points. And that's actually important for us because we want, chunky pieces of computation. So what happens is that our machine realizes that this computation is really expensive. It realizes that you don't need to worry about the incoming values of any of the local variables. And it realizes that linked list structures are actually predictable in a really fundamental way. Anyone ever written a memory allocator? Right? Okay. They're predictable, right? You know exactly how they're going to allocate memory. But rather than building a predictor mapped to your particular allocator, we're going to learn what kinds of chunks of memory your allocator gives us. And so essentially what ends up happening is we predict likely pointer values for these elements in the linked list. And each of those pointer values gets speculated on by one of the cores. And so the cores speculatively go ahead and try to compute this energy function. So what happens? Well, as I said, we're not the green line. That's how you know the data is real. What the red line says is if our cache lookup, right, if looking stuff up in the trajectory cache were infinitely fast, we would see the behavior on the red line. But we don't. We see the behavior on the blue line. And that's actually, the news there is pretty good. What it means is that there's a constant overhead for looking stuff up in the cache, but it's not all that bad. What does the blue line tell us? Well, the blue line says we scale pretty well up to about 256 cores. And then we don't scale so well, but we're still getting some benefit from them, right? The curve really keeps going up until between 1 and 2,000. And then it starts tailing off. So there's two things going on here. Guess how many elements there are in the linked list? Anybody want to guess? Between 1 and 2K. It's 2,000 exactly. So that's why we scale almost up to 2K. So that's good, right? We don't expect to actually scale much beyond that. And then why do we fall off the curve? Well, it turns out the reason we fall off the curve is an artifact of how we do our predictions. So what we ask our predictors to do is we tell the first core, predict what you think the state will be the next time you see this value. And then we tell another core, why don't you predict 2 time points in the future? And then we tell another one, why don't you predict 3 time points in the future? Now, this is a research, we actually don't reuse that computation. So the guy who wants to predict 1,000 points in the future actually predicts each of those 1,000 points, even though the guy who's predicting 999 has already done that. Not so clever. We can do better. But that's why those predictions fall off, is that as we add cores, some of the long-running predictions take a long time, and that's even not the problem. The problem is that we're running on a blue gene, and there's a synchronous barrier communication that makes us wait until the last guy has finished his speculation. So on one hand, you can think, boy, you're dumb, and that's fair. On the other hand, this is actually really good news, right? This is an implementation artifact. We can get around this. So the higher bit is we scale to like hundreds of processors, automatically, GCC, no magic, and we think we can do better if we sort of get rid of some of the stupidness. So that's pretty cool. But that's not the best result. So here's the really cool result. So there's this mathematical toy called the Collatz conjecture. And it is thought that if you take the following, any number, and apply the following series to it, it will converge to 1, but no one's been able to prove it. And so the series says, take the number, multiply it. If it's even, multiply it by 2. No, I'm sorry. If it's even, divide by 2. If it's odd, multiply by 3 and add 1. Don't ask me why. It just is. Anyway, the theory is that this converges to 1. So you might say, well, let's run it on a lot of numbers and see if they all converge to 1. So here's a very simple program that tests all the integers from 2 up to 100 million and says, essentially, do you satisfy the Collatz conjecture? Now, if I told you I was going to run this on a single core, what kind of speed up do you think I'd get? Like none, right? Because it's one core. You can't possibly get parallelization on one core. So this is one core performance on a laptop. And the green line here is normalized performance of 1, which is you run exactly how you would run sequentially if you didn't do anything. And what's really cool is that after a couple million instructions, we're actually getting performance better than single-threaded performance. Now, how could that possibly be? Right? Okay, good. People are laughing. This is good. Well, it turns out that the final sequence of numbers that get you to converge to 1, there's only a fixed number of them. Right? So for example, if you ever hit a power of 2, then you know, oh, I hit 1024. Well, that's going to go 512, 256, 128. Very predictable. So if any number between 1 and 100 million ever ends up at a power of 2 by doing this Collatz, we've seen that computation before. It's in our cache. We go to 1 immediately. So even though we're running on a single core, just by keeping track of this trajectory cache, we can actually get better than sequential, better performance without an additional processor. Now, I think that's pretty cool. And we also get the other kind of scale up too. So we also get multiple cores running and trying different numbers. The predictors take slower, so we kind of level off. But Amos really, really was excited that I was going to show a graph that actually showed this running on 16,000 cores. Right? Okay, and this really does. So we have access to this big blue gene machine. And yet, it doesn't go up a lot, but it's still going up. Right? How many programs have you ever run that scale to 16,000 cores with no programmer effort? Right? That's the really cool thing here, is that the program doesn't know anything about it. It's just the runtime. So I posed some questions earlier on. I said, you can't possibly guess points in the trajectory space. Well, actually, it turns out programs are somewhat predictable, so we can. And how on earth do you know when to check? Well, I've told you. If we pick these instruction point values carefully, then in fact, we know exactly when to check. But these states, how can you possibly compare all these states? Well, we compare them because they're not the whole state space. They're this very compressed representation. And a little secret I didn't tell you is that certain bits are more likely to match than others. So we even sort the bits in our vector such that the ones are least likely to match end up showing up first. So like the instruction pointer, things like that. We compare first so we can fail fast. So yeah, we can compare these states. Where do we store the trajectories? Right where you compute them. So it's a distributed storage project. And that's why it's really good to talk about here. And am I on drugs? No, as I said, just a little bit of scotch. So you could be saying, oh, come on, these are all toy problems. The answer is kind of yes and kind of no. So this physics problem is actually real. People care about it. Now, so they are real, but they are, in fact, in this class we call, embarrassingly parallel in certain ways. So yeah, so far we've run things that have very obvious structure. My theory is that the stuff the compiler people can do, that has really obvious structure too. And I think we can do those. Our hypothesis, and to be fair, we haven't proven this, is that there's another class of programs where there isn't necessarily static structure that the compiler sees, but there's runtime structure that we see. And we think we can exploit that. And the other thing is, there's nothing that says we can only exploit structure in our own program. So imagine for a moment a world where everybody's doing this. And every time you want to make a call into the C library, you say, has anybody else ever called this function with this parameter? And you get an answer back. That'd be kind of cool. So yeah, these are sort of toy, sort of real. Our VM is slow. It's all in software, yada, yada, yada. That's an engineering problem. You might say this dependency tracking, forget it. That's what transactional hardware does right now. So I'm actually really excited at the thought of building a little processor that builds on transactional memory, uses that for dependency tracking, and we actually put this thing in silicon. I'm still trying to talk my architecture friends into that. You need really good predictions, and you'll never do that for meaningful programs. Yeah, well, we don't need perfect predictions. We just need to be able to predict the dependent bits. And if there's structure in the programs, then we're pretty confident we can predict those. Couldn't you just do this all in the compiler? Well, Well, maybe. Maybe not, though. So we're exploiting both static structure in the program as well as runtime dynamic structure. And that's something the compiler can't do. So do we think there's a role for the compiler? Absolutely, right? It'd be nice for the compiler to point out, these good predictable points. The compiler knows that a lot of cases. So we're happy to let the compiler act as a recognizer and say, here are some good points you might want to try to predict. That's fine. Do we think the compiler can do everything? Not really. So, and it seems that this trajectory cache is potentially a problem. It's a distributed storage problem. What better place to present you with a really hard problem? My day is done. So, on that note, I am happy to take questions for as long as these guys let me keep talking, and at some point they'll pull me off. Yeah, go ahead.
How much overhead is involved in doing all of this? And how much do you have to be doing to be worth it?
So that's a great question. So the trajectory, we look for about 10 to the fifth or, tens of thousands of instructions between instances of the pointer on our prototype. Now, that's not any magic constant. It's going to be totally dependent on how quickly you can take advantage of these things. But you want these things to be chunky enough that you get a real bang for the buck. And then as your predictions get more certain, you might want to let your speculators run even longer. So you can imagine that some speculators who aren't really confident only run for, tens of thousands of instructions. But if you know that, tomorrow you're going to be here, you might actually want to let a speculator run for a long time. So we're talking about, tens to hundreds of thousands of instructions. Yeah?
How extensive are the modifications to the architecture that you've implemented virtually? Like, how hard is it going to be to convince vendors to implement these changes?
Yeah, so we got a lot of work to do before we can convince the vendors. On one hand, the architecture, it's an x86. On the other hand, it's not a full x86, like there's no floating point. So the execution engine, I don't think, is the hard part. The dependency tracking, I don't think, is the hard part because they're already doing it for transactional memory. And that's one of the things that makes me really excited about Silicon. So I don't really have a good answer to that question. I am hoping that in the next, while we could actually do a hardware prototype. I don't think it's going to be that bad. But it's easy to say that without having done it yet. Other questions? Yeah?
What has the least predictable trajectory?
Who has the least predictable trajectories? So I can't tell you that because we've avoided those. So where we are is that we've sort of gotten the infrastructure running. We know we can predict some of these ones with structure. And what we're really doing right now is saying, OK, do we want to have our own VM? Do we want to leverage somebody else's? How do we go to the next step so that we can take, my desktop environment and just run it? And so I don't know the answer to that. Yeah?
Do you assume all the cores are on the same machine and then they can all get to each other really fast?
Do we assume they're on the same machine? So the answer is no. So the experiments that go out to tens of thousands of cores are on a Blue Gene, and they are on the same. But I've got experiments on, a 30 rack cluster that are talking over local, gigabit Ethernet. So they don't have to be on the same machine. The way you tune your system in terms of how often you talk to your caches is clearly going to be a function of your communication latency. But the grand vision, and I try to tell my student this is the 10-year vision, not the PhD vision. But the grand vision is that all computers in the world just do this by nature and keep this, and then we all share computation. Right? Forget about the security problems for a minute. So no, there's nothing that says they have to be on the same platform, on the same machine. Right now, they have to be on the same architecture because of the way we're doing these bit vectors. You could imagine a world where we'd loosen that up, but we're not going there. Other questions? Yeah, how about back there?
Can you give us an idea of the sizes of the trajectory cache?
Oh, so the sizes of the trajectory cache. Wow, I should know that. It gets to be, so, basically at this point, it gets to be about the same size as the degree of parallelism. So if, it only takes us about 10 instances of seeing a particular instruction value to start making good predictions. And once we make good predictions, the entries that get put in the cache correspond roughly to the inherent parallelism. So if there are 2,000 elements on the linked list, there are roughly 2,000 entries in the trajectory cache. One more, OK. Oh, how to choose. How about right there?
So actually, about the security implications that you mentioned,
Yep.
Leaving aside the sharing computation side of it, is there any problem with running these speculators in sort of unknown construction pointers for?
So that's a great question. So what happens if you pick a point and it's, it's not a valid state? Well, then your speculation just crashes immediately. Yeah, we just throw them away. All right, I think I'm being pulled off the stage with the little, cane thing. So thank you all. I hope you have a great conference.